started out this part of calculus on the integral talking about area as the major problem. We haven't gotten to it yet, and now we're going to. We're going to define area as a limit. Before we can do that, we need a piece of notation that you may or may not have seen, but we'll introduce here anyway. It's the sigma shorthand for sums. Here is the idea. The idea is just that we need a shorthand for long sums that have a certain pattern to them. If we're looking at, so we want a shorthand for things like the following. If we're looking at 2 squared plus 3 squared plus 4 squared plus 5 squared, there's a definite pattern there. And you can imagine me going up to 100 squared or very large numbers. It would be nice to have some compact notation for writing this down. This is, in shorthand, written the following way. And I'll explain all of this in just a moment. It is written as the sum of the k squareds from k starting at 2 and going to 5. Now, all of this needs explanation. So let's go ahead and look at this kind of strange-looking piece of shorthand. It turns out to be very handy. Let me draw a very large version of it here. So this is going to be called the summation symbol. And we'll put AKs here, and I'll explain all of this, where k goes from, say, m to n. So first of all, what is this symbol here? Well, you probably have already seen this at some point in your life. This is the Greek S. And here it stands for sum. So that's what this is. This is a sigma, a capital Greek S, to be exact. Then, let's see what parts we want to talk about here. This number up top, the n, is called the upper limit of summation, or of the sum, if you like. And I put limit in quotes because this is not the same idea as limits, which we spent a lot of time earlier in this course discussing. This just means the upper bound, where the summation stops. But the word limit is used, and we have to get used to it. Then what does this a sub k represent? It represents the kth term of the sum. And what it represents really is some common form that all of these terms satisfy. So ak you might think of as a function of k. That's another way to think about this. As we do more examples, these notions will make more sense. If we look up in this example, you see that all of these terms are something squared. To be precise, a positive integer squared. Well, that's what this represents. This represents the form that all of these share, the common form. Well, if this was the upper limit, this m down here is the so-called lower limit of summation. So that's what this indicates. And then what is this k? The k that appears here is the same as the k that appears here, although I seem to have drawn it differently. There are many ways to write k. These are both the same k. So this is telling us how this varies. Same thing up here. K started with 2, so the first number was 2 squared. See, it's 2 squared. This says add the next number. So when k is 3, this is 3 squared, we've added 3 squared. Then k moves on to 4, and then it stops at 5, and we add 5 squared. So that's how this is read from this. The summation says you put pluses in between the terms, and this says where the k starts and where it ends, proceeding by integer jumps. So this is called the index of summation. And it is, of course, it stands for an integer, so it's really an integer index of summation. And what kind of letters can be allowed here? Well, k is allowed, certainly, and other letters near the middle of the alphabet, something like I, J, K, L. These are the traditional letters that are used here. Technically, any letter can be used. But if you want to have other people understand you, you probably want to use some of these conventional letters. So that's what this summation means. Let's look at several examples so we can get the hang of this. Suppose we want to write 1 plus 1/2 plus 1/3 plus 1/4 in shorthand as a sum. Now, certainly, it's not very useful to do that for only 4 terms. But if you had 400 terms, you'd probably find it useful. This would be the sum, sigma for sum, of all the things that look like 1 over k. That's what all of these look like. Even the first one, which can be thought of as 1 over 1. Where the k starts at 1 for the first one, then moves through 2, 3, and 4, and stops at 4. This is one way to write this down. The k was completely an arbitrary choice. I could rewrite this as the sum of the 1 over i's for I equal 1 to 4, and I've said the same thing. Both of these are correct shorthand for this. The k, the I, the j, these are just letters that you choose depending on circumstances. Okay, there's one example. Let's look at another one. Suppose I want to analyze this sum. Suppose we take the sum of 2 times k, where k goes from 3 to 6. Now notice here, when I have more than one term, as we do in most situations like this with integrals or derivatives or even limits, I tend to put parentheses around it just to make sure that I'm saying this summation goes over this entire set of objects. So what does this say? This says it's 2 times k, where k goes from 3 to 6. And what do you do in between? You add. So 2 times 3, because k starts at 3 is the first one, then I add, that's what the summation says. I go to the next number, the next integer, which is 4. So this is 2 times 4 plus the next integer, 2 times 5, and I keep this up until I reach this final integer, which in this case is just the next one, 2 times 6. Now this sum here can be simplified, yes. You can multiply it out and add it up and get a single number. But that's not the point here. We want to see how the summation symbol works and how to interpret it, and this is how to interpret it. Let's go ahead and do one that looks much more complicated. Here k will go from 0 to, say, 3, and it will be minus 1 to the k as the term inside, times 2k plus 1. Let's see how this works out. This may look all complex to you, but as you'll see, there's a neat pattern in here that's easy to see once you start playing with these. So let's just go ahead and make the straightforward substitutions. The first integer is 0. We put it in for k here and here. So we will have minus 1 to the 0 times 0 plus 1. 2 times 0, of course, is 0. Plus minus 1 to the 1 times, now k is 1, so it'll be 2 plus 1. Plus minus 1 squared, that's when k is 2, times 2 times 2 is 4 plus 1, plus minus 1 cubed, and that's the last one. And then in here it will be 2 times 3, which is 6 plus 1. Now let's simplify this just to see what pattern really lives here. Minus 1 to the 0 is 1. 0 plus 1 is just 1. Here we have minus 1 to the 1, so the negative is remaining, times 3. So this is minus 3. Minus 1 squared is a plus. This is 5. Minus 1 cubed is another minus, and this is 7. Look at this really nice pattern. It is the odd integers starting at 1 and alternating in sign between. Now that's something that you might not have seen directly from here, but with experience you can, because this is a standard way of writing an odd number. And I will tell you a handy fact about this, power of minus 1, which will turn out to be useful in many circumstances, so it's good to know. Minus 1 to the n, and this is obvious, but one of those things that once you see it you realize how useful it is. Minus 1 to the n. It's either minus 1 if n is an odd integer, or it's just 1 if n is an even integer. So this is a way of writing down a sum where you really are alternating between plus and minus signs. And we will use this again. All right, let's look at a couple of other notes about the summation notation. Suppose we're adding up x cubed, where j goes from 0 to 2. Now, you may pause and say, wait a minute. There's no j in this expression. And you're right, there is no j. So what could this possibly mean? If the object that you're adding has none of the letters involved here with the index, so there's no j in this case, or no k, l, and so on, then that means this is just what you add this many times. That is to say, if there's no j, what we do is look at here, and we're going from 0 to 2, so that's 0, 1, 2, which means we have 3 terms. And therefore, we will add up x cubed 3 times. So the summation sort of reduces to just adding this object, which doesn't change as the j changes, as many times as the summation indicates. So this is 3 times, so this is going to be 3x cubed. Okay? That's how that works. Let me do one more of the same type. Suppose someone asks you to take the sum of 5 from n equals minus 2 to 3. Now this can be a little disconcerting at first because you feel like the minus 2 ought to be somewhere in here, but it isn't. All that this indicates here, since there is no n in this case involved with 5, you're going to add the 5 up as many times as you have integers appearing here. Now, how many integers do we have? -2, -1, 0, 1, 2, and 3. So that's 6 terms. So that means we're going to have 5 plus 5 plus 5 plus 5 plus 5 plus 5. 6 5s, of course, is 30. But that's what this means here. When there is nothing in here involving the index of summation, then you just add this object up as many times as you have integers appearing in the summation. So there's nothing multiplied by -2 or 3 here. They're just an indicator that there are 6 things here. All right, here is something else about summation. Often we want to change the limits of summation. Perhaps we're trying to add 2 summations, and one of them starts with n equal 1 and the other one starts with n equals 0. We'd like them both to start at the same place so we can just add them straight across. How do we go about doing that? Well, I'll show you that with this one example. Express this summation, 5 to the k minus 2 power from k equals 3 to 6 with a lower limit of summation being 0. So you see it starts here with k equal 3. I want to change this so it's starting with 0, not 3. So how do I go about doing that? Well, generally when that happens, until you learn some more technique and you start fiddling with the letters, you probably ought to just write it out and see if you can rewrite it starting with some index that starts with 0. So that's what I'll do here. This is equal to 5, let's see, 3 minus 2, that's going to be 1, plus 5 to the 4 minus 2, which is 2, plus 5 to the 5 minus 2, which is 3, plus 5 to the 6 minus 2, which is 4. So this sum represents these 4 numbers added. I notice that what's happening as I move from place to place, that there's a pattern that I can see. And the pattern is that it adds 1 power to each term. So this was 5 to the 1, then I go up 1, 5 squared, up 1 to here. So that suggests that perhaps I could write this as nothing plus 1 as the power, plus 5 to the 1 plus 1, plus 5 to the 2 plus 1, plus 5 to the 3 plus 1. So it seems like I have a nice pattern, which means I can now write this as a sum of 5 to the k plus 1 if I want to use k again, where k starts from 0, see it's 0 here, then it's 1, 2, and 3, and ends at 3. So this summation, although it looks very different from this one, both in the powers and in the values for k, represent exactly the same number. And keep that in mind. That's just one of the things you need to get used to as you work with sums. We have the summation notation. Now it's time to look at some of its properties. Let me go ahead and tell you about the basic properties that will help you in working with sums. First of all, this is going to be something that's very familiar. This theorem says if you have a sum of c times a sub k's, the a sub k's are terms that involve k, and the c does not involve k, then, as you might expect from your past experience, the c comes out front. This is c times the sum of the ak's, k equal 1 to n. And all that's required here is that c is not a function of k. Doesn't involve k in any way. So you can pull it out front. It's not affected by the summation. Then these other two are ones you can also probably guess. If I take the sum from k equal 1 to n of ak's plus bk's, then that indeed is the sum of the ak's, k equal 1 to n, plus the sum of the bk's, k equal 1 to n. And likewise, it works for differences also. If you have the sum from k equal 1 to n of ak minus bk, then you have the sum of the ak's, k equal 1 to n, minus the sum of the bk's, k equal 1 to n. And my question for you here is, does this look familiar? Well, it should. These properties, that the constant comes out front and that the object here in the case of sums breaks over summations or differences, is exactly the same set of properties that works for limits, it works for derivatives, and it works for indefinite integrals that we've seen. So this set of properties should be so familiar that extending it to summations should not be any difficulty. Now let's do a theorem that's a bit more interesting, something I think you'll find fun to look at. Suppose I want to add up just the k's, where k goes from 1 to n. What does that mean? That means 1 plus 2 plus all the way up to n. I want to add those numbers up. Now that's going to turn up fairly often. It turns out, and I won't do the proof here, but you can prove that you don't have to have a summation like this, where you have this index letter going from 1 to n, you have this sum written out with this ellipsis in the middle. In fact, you can write this simply as n times n plus 1 over 2. Whatever this top number is n times n plus 1 over 2. That will give you this sum every time. This is what's called an open form. Either one of these represents the sum correctly, but not very nicely, whereas this one is what's called a closed form. There are no ellipses in here, there's no summation symbol, it's simply a number involving this number n. So this is preferred whenever possible, and it is useful in a case like this. Now remember, we're starting at 1 here, k equal 1. So this formula only works if you go from 1 to n. If you start anywhere else, this is going to have to be modified. All right. The other kinds of sums that are very common is not only adding k, but adding k squared or k cubed. So let me write those down. Again, I won't prove these, but you're going to want to commit these three sums to memory. So if you add up the sum of the k squareds, which is 1 squared plus 2 squared up to n squared, that turns out to be n times n plus 1. Well, so far it's exactly like the previous one. But then you have another factor, 2n plus 1, and it's all over 6 instead of 2. Finally, and this will be nice, the sum of the k cubes from k equal 1 to n, which is 1 cubed plus 2 cubed up to n cubed. This one turns out to echo the first one. In fact, it is n times n plus 1 over 2, quantity squared. So really, if you learn the first one and the second one, the third one comes almost free. And remember, every one of these starts with 1. So if you're adding up any of these forms, you now have closed formulas for reducing the summation or this long sum to a single item. Let me show you an example how this might be used. And we will do things like this later. Suppose you're summing k times k plus 1, where k goes from 1 to 30. Now, when you're getting to numbers like this, it becomes very tedious to write it out and just add the numbers up. So we like to have these formulas that we just developed. The formulas involve powers of k. Well, here I don't have any powers of k, so I'm going to multiply this out so I can see them. So this is k equal 1 to 30, and in here I have k squared plus k. Okay, well, that becomes the sum of the k squareds from k equal 1 to 30, plus the sum of the k's from k equal 1 to 30. We have a formula for each of those. If you recall, for the k squareds, it was n, which in this case is 30, times n plus 1, 30 plus 1, times 2 times n plus 1, all over 6. And this one was n times n plus 1, all over 2. And if you do the simplification, which I will leave to you to do, is 9,920. But the point of this is not getting this answer. The point is understanding how to simplify this sum into these two nice closed forms. That's what those formulas are used for. We have one more set of facts I want to tell you about that use our notion of limit that we've talked about earlier in the course. These also will turn out to be very useful. Suppose you're taking the limit as n goes to infinity. And we need to talk about this for a moment, but not too long. When we saw limits before, we always had letters like x or y or t going to infinity, where the letters pass through all the real numbers on the way to infinity. This is a fundamentally different kind of limit. It's where n is going to infinity, but only passing through positive integers. Or if it starts with the negative integers, eventually passing through positive integers. So it goes from n to n plus 1 to n plus 2 and so on. This doesn't materially change any of the limits we'll be doing. But you should note that there's a difference here, and at some point in the course, it may make a difference. Suppose I want to take the limit of 1 over n times the sum of the 1's from k equal 1 to n. Turns out the answer here is 1. Well, this limit is very simple. It's only here to see it as part of a pattern of 4. Because if you're adding up 1 here, and you're going from 1 to n, that means add up 1 n times, which gives you n. n times 1 over n is 1. Limit of 1 is 1. So there's really nothing to learn from the first one. The second one is where things get interesting. If I take the limit now as n goes to infinity, and I do 1 over n squared, see here, this is 1 over n, this is 1 over n squared. The sum of the k's from k equal 1 to n, where I'm adding k now instead of just 1. This turns out to be 1/2. And this one I will show you the proof for, because it's quick and it does remind you of some of the things we saw with limits. Inside here, I have 1 over n squared. This expression has a closed form, which is n times n plus 1 over 2. There's an advantage of the closed form. If I multiply out the top, I get n squared plus n. If I multiply the bottom, I get 2n squared. Now, as n goes to infinity, where does this head? Well, if you remember when we took limits of rational functions, which is what this is, we had x's, of course, but the same rule applies here for n's, that if the degree of the top is the same as the degree of the bottom, then we just get the coefficient of this n squared over the coefficient of this n squared. In this case, we get 1/2, which is what we expected. This is as n goes to infinity, and this is because this is a rational function. So we really are pulling in here some of what we learned before. All right, I won't prove the others, but you can see where this is headed. As n goes to infinity, if I do 1 over n cubed and I add up the squares, k squares from k equal 1 to n, you might expect I'll get 1/3, and you'd be right. And then finally, as n goes to infinity, if I do 1 over n to the 4th and I add up k cubes from k equal 1 to n, I am going to get 1/4. Now these are just limits that you want to put in the background and remember that they exist. We will come back to these and use these eventually. Finally, it's time for definition of area under a curve. This is what we've been heading toward. Let us do a little development here. And this will call to mind what we did at the very beginning of this part on the integral. Imagine we have a curve like so. So we'll limit ourselves still to a function f of x which is continuous. So there are no breaks. And we'll assume that f of x is greater than or equal to 0. As I've drawn it, it's above the x-axis. And let us imagine here that I have a point A and then another point over here, B. All right. What we want to do is find the area in here, and we want to use what we know to get there. So we'll break this up into rectangles as we've done before. Here is the process. We will look at this interval, and we will break it up in some manner into equal parts. So if I call A x sub 0, and then maybe the next one will be x sub 1, the next one will be x sub 2, the next x sub 3, and so on. We'll continue here. Then B will be x sub n, the last one. The one before B will be xn minus 1. The one before that will be xn minus 2, and so on. So now we will break this up. And this distance, which we'll be looking at in a minute, is of course b minus a, the right minus the left. And so what are we doing here? Just to write this down. We are partitioning this into n equal subintervals. Now the conditions that f is continuous, that it is above the x-axis, and that the intervals are equal will turn out not to matter in the end. The theory is more general than this. But for now, we'll go ahead and stay with this. And each width, well, what do I mean by width? Well, each of these partition pieces, if we imagine them slicing upwards here, to slice up this region, before we get to the point of creating rectangles, there's a width here on the bottom, and they're all equal. Each width is going to be what? It's going to be 1/n of the entire piece. So 1/n of b minus a. And that is often written as delta x. So there's a piece of information. So here's what we're headed toward. And what we need to now do is look at these slices and approximate them by rectangles, as we've done before. So let me lay that out. So what we'll do is we'll choose any point in each subinterval, and that's any point whatsoever, and you'll see why, to calculate rectangle heights. All right, here's a really big picture of a small part of what we were looking at. Imagine here we have xk minus 1. Here is xk, and here is xk plus 1. So there were some before, perhaps, and some afterwards. So we're at a typical place in the partition. And imagine that we have sliced vertically from each one of these. So there are our slices going straight up. Now, I want to pick in each one of these regions an arbitrary point. So maybe I'll choose this point here, and I will call this one xk star. And then in the other one, I'll pick another arbitrary point, and I'll call this one xk plus 1 star. Now, what do those give me? They give me a place on the curve that I can use as the height of the rectangle. That's what they give me. So this one here gives me a point like that, which gives me a height like that. Now I have two rectangles here. And I can figure out their areas because I know their widths. They're identical, and I did those on the previous page. They're delta x, or 1/nth of b minus a. What are the heights? This height here will be f of xk plus 1 star, because that's what I use that xk plus 1 star for, to give me a place on the function. And then this one here will have height f of xk star. So with that, remembering then that I will be choosing these k star and k plus 1 star points in every interval, I now am set up for writing down an approximation to the area under the total curve. It will be the sum of the areas of all these rectangles. So the area under the curve, which is what we really want to get, is approximately equal to, well, let's see. The area of one rectangle is fxk star times delta x. This is the height, this is the width. Then if I add these all up, where the k's go from 1 to n, I'm adding the rectangles all the way up across the region. This, which was the area of one rectangle, now is added up for all n rectangles, and that's a good approximation to the area under the curve. We want to know how to get better. Well, it seems that if I had more rectangles that were thinner, where the bases were smaller, with heights chosen in the same way, I ought to get a better fit. And if I increase that infinitely far, I ought to get a perfect fit. And you saw that when we looked at this earlier. So I can right now write down a definition which seems reasonable. If f is continuous, that's one of the things we're assuming here, if f is continuous on the closed interval AB, and f is above the x-axis on AB, as we saw in the previous picture, then I can actually write an expression for the area under the curve using the sort of notions we've developed so far in this course. Area under y equals f of x over the interval AB. That will be defined here to be the limit as n goes to infinity of this expression. So I have the sum from k equals 1 to n, and I'll leave out the inner brackets here just for convenience, fxk star times delta x. There it is. We have now found the answer to the area question when we have a continuous function over a closed interval and the function's above the x-axis. So we're going to want to eliminate some of these restrictions later. But this is what we have. Now we'd really like to get a better way to do this. In the same way that we defined derivatives originally as a limit and then eventually ended up developing rules for them, we will do the same thing here. That will come later. But for now, let's go ahead and do an example of this so we can see how all the details work themselves out. Here's what we're going to do in this example. we're going to use the definition we just wrote down with, and now we have to choose a particular x star. We'll just choose x star to be the same thing in every interval. It will be the midpoint of the, so the xk star will be the midpoint of the kth subinterval. So we'll choose the same corresponding point in each subinterval because it doesn't make any difference, and this makes it more convenient for us in calculation. And we'll use that to find area under, let's see, what curve? How about f of x equals 9 minus x squared over the closed interval 0 to 3? First of all, let me draw a quick picture so you'll see what we're doing. This is the standard quadratic parabola flipped over and shifted up by 9. So it looks something like this. Here's 9, crosses down here at 3 and minus 3, and this area here is the area we're about to calculate. So here is the beginning of our solution. Well, let's recall the formula from the previous page so we know what we're trying to do. The area is the limit, as n goes to infinity, of the sum from k equals 1 to n of the f of xk stars delta x's. Seems like a lot, but what we really need to find is what delta x is. That will be the same for each interval because we're breaking it up into equally spaced subintervals. And then we need to find out what xk star is and evaluate f of xk star. Once we have that, the rest of this is just calculation. So let's address those issues right away. First of all, what's delta x? Well, by definition, it's 1/nth of b minus a, the length of the interval. Well, b minus a here is 3 minus 0, so that's just 3. So this is 3 over n. So delta x is 3 over n here. Now, to work our way toward xk star, I really need to have a form for xk, which I don't have yet. So this is a note that can be used in other problems too. Notice we took x naught to be a, which was the left endpoint, which in this problem was 0. Then x1 was the left endpoint plus the distance, the equal distance we travel to get to the next point. So x naught plus delta x gives me x1. In this case, that will just be delta x because x naught is 0. Then x2 would be x1 plus delta x. x1 is delta x, so if I add another delta x, I have 2 delta x's, and so on. So in this problem, it looks like if I go down as far as xk minus 1, I'm going to have, let's see, this was 2 and a 2, a 1 and a 1. I'm going to have k minus 1 times delta x. So let's take that, and from that, I will be able to get my xk stars that I'm interested in. To get xk star, here is the picture. We're talking about xk minus 1 to xk being the subinterval in question. We know that the distance of this interval is delta x. We also know that in this problem we're choosing xk star to be the exact midpoint. That's our choice. So the form for xk star, we need this to do the calculations. Xk star is going to be xk minus 1, this point, plus half this total distance, plus 1/2 delta x. Well, let's see. xk minus 1 we did on the previous page. That was k minus 1 times delta x, plus now this 1/2 delta x. Put this all together. This is going to be k minus 1/2 times delta x, a little bit of algebra. And now remember what delta x was. That was 3 over n. So this is now k minus 1/2 times 3 over n. And now we've got xk star. The next thing to do is evaluate xk star using the function f. And we'll work our way toward the final limit we're looking for. So f of xk star times delta x. This is the area of one rectangle, remember. And we know xk star now, so we can do all of this. So what is this? F of x was 9 minus x squared. So this is 9 minus xk star squared times 3 over n, which is what delta x was. Well, we just figured out xk star. And let's see, I wrote this with the square on the outside. That's not right. The square goes on the inside. It's xk star squared. We'll see that in this next expression. It's 9 minus k minus 1/2 squared times 3 over n squared times 3 over n. And then, with algebra that I will not show you, but you can do on your own, you end up with 27 times 1 over n minus 1 over n cubed k squared plus 1 over n cubed k minus 1 over 4n cubed. That is the area of a single rectangle. And now we're going to add this up over all the rectangles and then take the limit, and we will be done. So let's go right to it. We take the limit as n goes to infinity of the sum from k equal 1 to n of f of xk star delta x. This is going to be the area when we're done. So we substitute in that expression for that one rectangle from the previous page. There was a 27, remember, which we can pull all the way out front. And so we end up with 27 times the limit as n goes to infinity of, and here's what happens inside, 1 over n times the sum of the ones from k equal 1 to n, minus 1 over n cubed times the sum of the k squareds from k equal 1 to n, plus 1 over n times 1 over n squared, you'll see why we did that in a second, sum of the k's from k equal 1 to n, minus 1 over 4n squared times 1 over n sum of the ones again from k equal 1 to n. And this is the end of my brackets. Well, by the formulas we looked at before, the sum of these ones times 1 over n is all equal to 1. 1 over n cubed times this turns out to be just 1/3. Here, this expression here will turn out to be 1/2, and this expression here will turn out to be 1. Now these are in the limit after we've taken the limit, and what will happen next? We'll have 27 times, and from here we'll have a 1. From here we'll have a 1/3. From here, this part went to 1/2 under the limit, but there's a 1 over n also, and the 1 over n, of course, goes to 0, so this goes to 0. Likewise here, this goes to 1, and now this goes to 0, so this entire last expression goes to 0. So I have 2/3 times 27. In other words, I have 18. Now that was a very long example, and we will find out how to take this limit without going through the limit process and actually working this out in detail. We want a faster method, and we will get one eventually. That will be coming up later on. Now we'll look at the notion of net area. What could that possibly mean? Well, area, remember, by definition, is a positive number. Net area is going to take into account that the area or the object that is calculated by an integral may be positive or negative. Sometimes this is called net signed area, plus or minus sign. Here's the idea involved, and it really seems natural when you think about it. If you extend your notion of a continuous function beyond one that's just above the x-axis, then you might have something like this. And maybe here is your point A, and here is your point B. Now, if you do what we just did and break this up into a partition, build rectangles, notice that here you end up with a positive number, area, because the f of x height is positive, and of course all the widths are positive. The same thing happens here. But what about this part down here? Down here, you end up with a negative number. That's because each one of the rectangles, if you multiply the height here, which is really a negative height, you end up with a negative number. Let me show you a little bit more visually here. We have a piece of the curve, and we're above the x-axis. And I compute f of xk star times delta x, which is the area of this one rectangle here. Then this is a positive number because we're above the x-axis, so this product is positive. The width, of course, is always positive. However, if we are below, when we build our rectangle here, then the same expression, f of xk star delta x, is now less than 0. Why? Because the f values go down. So when we add these all up, when we get a limit, we're going to get a negative number. Well, that can't be area because area has to be positive. So we call it negative area, or we call it signed area. And it's going to be net area because you're taking the positives and adding it to the negatives, and there's going to be some net result, which is not going to be the total area of the top and bottom combined. So here is the definition we'll use. This is the net, sometimes called signed area. This is what a limit actually gives you if you don't know that the function's always above the x-axis. Again, our functions are only continuous, but that's okay. We'll deal with other ones later. If f is continuous on a closed interval ab, and notice here that the point is that it is not, we're not assuming that f of x is greater than or equal to 0, as we did before. Then, when you take that limit, which again we'll give a better name to later, we take that limit where k goes from 1 to n of f of xk star delta x, which is the actual area under the curve. Then what you get is that you get a net signed, and what I mean by that is plus or minus sign, area. And as the area between y equals f of x, the curve, and on the x-axis AB. So here's what you get through that process. And what you need to know is that when the f of x's are going down, the little rectangles that are built to create this limit are negative. And when you have a combination of negatives and positive, you don't know what you're getting. You're not actually getting the area that it would take to paint these three regions. What you're getting is the arithmetic sum of them, which is then the net area, or the net signed area. What if you can't find that limit? What if you can't actually calculate the area under the curve in the way we've decided to do? Well, sometimes you can approximate that area. And there are many techniques for approximation. You'll learn some of them later if you go on in calculus. One of the simplest is the one we've already developed, using our rectangles. So we can approximate area numerically by just making the following observation. For large values of n, that limit, which represents area or net area, either one in this case, of f of xk star delta x, if your n is large enough, then the limit and the summation up to that very large n are approximately the same. Because the limit as you go to infinity is the number that you get here, and if the n gets very, very large, it's virtually close to infinity for practical purposes, so whatever you get out of this will be approximately equal to this. Now, of course, you'll have to choose the right end to get as close as you like, and you'll also have to choose a way to calculate the xk stars. Now, we choose a convenient way to do that. You saw us do that in one example, but generally, you get to choose your xk stars, so you choose an easy one. So let me just give you an indication of that. Choose easy xk star points. Say, you might let xk star, and let's just draw a little picture here so we can keep in mind. Here's xk minus 1, here's xk. So the xk stars come from in here. You might choose xk star to be xk minus 1, which is the left endpoint. That's easy. You might choose xk star to be xk, which is the right endpoint. Also easy. Or for some reason, you may feel better choosing the midpoint. The midpoint is the average between these two, so it's 1/2 xk minus 1 plus xk, and that is the midpoint. Any one of those can be used, and you just choose whichever one is computationally simplest. You evaluate f at those numbers, you multiply it by, well, when you have b minus a and you have the n, you can figure out delta x, which is 1/n of b minus a. Then you add them all up. A computer program can help you do this. A calculator can help you do this. And the number you get is an approximation to this area. And there are several problems in whatever text you're using that will allow you to practice this. And you should do that at this point. We will come back to these ideas later. A few exercises for practice. I've actually pulled the exercises I want here all into one big one. We'll just call this one exercise, but it has 3 parts. First of all, and these are all ones that involve summations for you to practice. Evaluate the following sum. From k equals 1 to n, 5 over n minus 2k over n. As part B of this, I want you to solve the following equation. The sum of the k's, where k equals 1 to n, equals 465. Finally, another summation of a different kind. Evaluate the sum from k equals 1 to 100 of 2 to the k plus 1 minus 2 to the k. Give those a try. Let's look at part A first. Here's the summation you were looking to evaluate. Notice that k is the index of summation. N is simply the final number that the index goes to. So anything in here that does not involve k is not affected by the summation. So I can write this by breaking this up into 2, it's a difference, and then here I can think of 5 over n as a constant to be pulled out front. Here I can think of 2 over n as a constant to be pulled out front, which means I can rewrite this as 5 over n times the sum of the 1's, can't forget the summation there, sum of the 1's from k equal 1 to n, minus 2 over n, the sum of the k's, because that's all that's left here, k equal 1 to n. Now we use our notion of the closed form to simplify further. This is 5 over n. Here, if we're adding 1 up, let's see, n times, I just get n. Minus 2 over n, if I'm adding k up n times, this is where the closed form that you memorized will come into play. This will be n times n plus 1 over 2. Then I simplify further. 5 over n times n is 5, minus, let's see, the 2's and the n's go away, minus the quantity n plus 1, and I end up with 4 minus n. That's what you should have gotten as the simplified version of this first problem. Let's look at the second problem now. This was part B. Here you asked to solve the following equation. Sum of the k's, k equal 1 to n equals 465. Now, the first thing you should ask yourself when you see a problem like this is, solve for what? It appears that there are 2 variables here, k and n. But that's really deceptive. There's only one variable here, n. K is the index of summation. Once this sum is summed, the only thing that will be left will be n. So to solve this means to solve for n. Now, I'll need to simplify this to get at it. Luckily, this is exactly a sum we've seen before that has a closed form. The closed form is n times n plus 1 over 2, and that equals 465. That is really the only step involving a summation here. The rest of this is just plain algebra. So we can quickly run through this so you'll see what it is. N squared plus n is equal to 930. That's n squared plus n minus 930 is 0. This factors nicely. N minus 30 times n plus 31 is 0. And so that means n is equal to 30 or minus 31, which it cannot be, of course. N has to be a positive integer here. So n equals 30 is the result. The only real summation step was the first one, and I wanted you to think about what you had to solve for. The third one also shows something about sums that's worth knowing. In this one, the summation was k equal 1 to 100, which it certainly should raise your eyebrows, 2 to the k plus 1 minus 2 to the k. Now, if you were to try to write this out 100 times, you'd really feel that that was tedious. And these are not expressions that occur in any of the formulas we learned. So there must be some other way to attack this. Let me show you what happens if you start writing this out. We'll write up the first few and then the last few and see if we can detect a pattern. Let's see, if k is 1, we have 2 squared minus 2 to the 1. Added, because this is a summation, when k is 2, I have 2 cubed minus 2 squared. Plus dot dot dot, plus, and let's go to the end. The one second from the end is when k is 99. That would be 2 to the 100th minus 2 to the 99, plus the last one, which is 2 to the 101 minus 2 to the 100th. Now, if you look at this carefully, you see something very nice is happening. Notice there's a 2 squared here and a minus 2 squared here. Those add up to 0. So the first one in this expression and the last one in this one add to 0. So the first one in this expression and the last one in the next expression, which I haven't written, will add to 0, and so on. First one here, last one here add to 0. First one in the one right before the end and the last one here add to 0. So this means that I end up with 2 to the 101, that's from here, and I have this other one minus 2 to the 1. And that's it, folks. That's the end of that problem. This is what's called a telescoping, or sometimes it's called a collapsing sum. because although it appears that you'd have to write this out 100 times, in fact, all the intermediate terms cancel each other out, and you're left with one near the beginning and one near the end. This is worth keeping track of. Now, this will not happen all that often, but when it does happen, it's really worth using. So, having practiced these, you are ready to do some of the problems involving the limits, which we've just seen.